uh, this session of the workshop on asynchronous hyperproperties. My name is Ezio Bartocci. I'm here a professor at Vienna for Physical Systems. So for this reason, probably they asked me to chair this session on CPS. So our speaker today, we have the pleasure to have Ashutosh Trivedi from University of Colorado Boulder. He's an associate professor now, right? And he did his PhD in Warwick University, UK. Then he did his postdoc in Oxford and the UPenn.
Yes.
Then he was for a period an assistant professor at the Indian Institute of Technology in Bombay. And then later he moved to University of Colorado Boulder. And the topic is very interesting, at least for me, that I'm in CPS, because it's the application of hyperproperties in the field of cytophysical systems, ranging from fairness, privacy, metamorphic testing, and also legal requirements. So I leave you the stage. Thank you for this.
Yeah, thank you for the introduction. Okay, so let me quickly check. Let's get started. So each and every one of you present here today care deeply about developing high quality hardware, software, or cyber physical systems. These systems could be mission critical. These are safety critical. Over the last 40 years, collectively, we have been working on formal methods to improve safety of such systems. Right? We have been working on formal logics to express properties of the system. So it's like a central thesis of formal methods. Every step of the development of the system, we have to write logic that will continue to refine. So logic is like a common piece for the application of rest of the formal methods. But once we have the logic, we have been developing this powerful techniques like automated theoretic verification, abstract refinement, inductive variants, things like variants. Right? Along those techniques, we have powerful algorithms like symbolic model checking, bound model checking, set solvers, and so on. And with that, we have been working on also tools of different kinds. Powerful tools to do model checking like NUSMV, like Father, Flowstar, or Prism model checking. But more recently, we have been seeing something. Let me just stop the recording part because that takes. So more recently, we have been seeing a change in the way people are writing systems. More and more of these systems, they are data driven. They are written by having components inside which could learn from data. Right? It could learn from data of the kind of input output, or more like reinforcement learning, some kind of a learning agent is sitting inside that. Right? You could think of these components in the form of perception modules for your self-driving car, right? Or they could be neural controller, they could be neurosymbolic programs, or they could be large language models. And this has been quite powerful. This has kind of allowed us to dream about self-driving cars, because now your neural networks could see for the first time. We are still interested in these systems, in safety of such systems, but again, bunch of properties that we were not so much concerned about, they are becoming more critical, right? As this new generation of cyber physical systems, they are getting more and more part of our social infrastructure. We have to be bothering about things like privacy, whether the functions of our system is not leaking some crucial information, some confidential information about the system that we are not comfortable with. Right? We have to bother about fairness, because these components, neural networks, and all of the machine learning, they learn from input-output data, historical data. Right? We do not want these modules to encode and maybe increase the discrimination which is present already in our inside. Right? Then we have to be also make sure that these systems are legally compliant. Right? I will try to give some of the examples from privacy, fairness, and legal requirements quickly to kind of motivate you to see what kind of specification you will be requiring for this properties that go beyond your safety concern. Of course, we know fairness, privacy really well. Fairness you could see, but then also some legal specifications are quite interesting. So let's take this very first quick motivating example about privacy. Right? Here I will take a simple example of designing, let's say, a smart hospital. Right? And you would like to see that concerns, they are beyond differential crisis in a very weird fashion. Just take a simple example, right? Assume that you are designing a smart hospital with various sensors inside and so on, and your goal is to make sure that the patients are satisfied with the service, right? So you would like to minimize the time that they are waiting in different operations in the hospital. And so what happens typically in your visit to a hospital, you go to a nurse, you stay for some time, they take your weight, then you would go on with other kind of essentials, then you would go to wait some more time, meet your physician, do some other things and so on. Right, so what if we could kind of collect the different timings of this event and try to ask the patients why they're visiting this hospital, right? And using that, we would like to kind of make sure that the person is done with. Something similar has been done in Toronto in late 90s, I suppose. So there was this paper written by Wendy Nelson and others, and she's now program manager for NSF for smart and connected communities. So this data that they release is essentially private, right? What they are doing essentially, quickly read this one. Why the patient is visiting that particular clinic and how much was a different time, how much time they spent with the nurse, with the physician, and they're kind of releasing this overall trend of this system, right? From 90s. Now you can take this input data set and you train a very simple decision tree. And you could see from this decision tree what is happening is that if you are going to that hospital and you spend like very close to 5 or 6 minutes with the nurse and then spend like 30 minutes, about 30 minutes with the physician, with high probability you are going for a psychotherapy session. So it's the data that they released was differentially private. You cannot tell, looking at the data about something about the person on which data was collected. On the other hand, it released the information about all of the patients that are going to go in the future in a very systemic fashion. It's a systemic leak that can tell, information about the whole timing signature of that particular process. Non-interference traditionally is one of these canonical properties that we formalize these specifications for. Simply put, inputs differing only in their confidential aspects, right? They are going to show us exactly equivalent observation or some modification of that, they're epsilon close, so that you're not leaking any information. And you could write that formally using something of this sort. Let's take the next class of specifications. These are fairness specifications. So typically machine learning by definition, they work with some historical data, then they train a model, and we take these models and put inside our hardware, software, or cyber-physical problems, right? We would like to make sure that these models, because of their nature, they are known to find simple patterns in the system, stereotypes in the system, right? We want to make sure that stereotypes that exist, we know in our society, they are not continue to propagate inside the next generation of devices that we are going to make. How do we do that? And the first thing is, do we really need to bother about this hypothetical significance? Right? For that, I will take this example from US criminal justice system. You may have seen this example. Right? Here is this software called Compass, and this has been used and still being used in the US across various states to provide a label to the criminals itself. So it's like how likely they are to offend again. And they are using a data-driven system, which is a mild term to say it's like a neural network behind somewhere, right? What you would expect from any system like this, that criminals who are getting high rating, they may have a bad record, or they are for some reason more likely to offend in the future, right? ProPublica is an investigative journalism organization, and they looked into this system and found that these are systemically biased against black individuals by finding very concrete data, right? So here is an example of 2 petty theft cases. The first one is a low-risk individual, second one is a high-risk individual, right? And if you would click on and see what they have gone to do and what was their history like before we got those risks, the first one has more severe prior offenses and continue to do some subsequent offenses as well, unlike the second individual. Similarly, these are the drug possession arrests. The first one is low risk individual, second one is high risk. And then you would see the first one, again, the similar trend continues in this case, right? You may define different semantics of fairness, but if you look at data of this form, then you know that something is going on which is not fair inside. ProPublica maintains still that the black defendants, they have high false positive rates. On the other hand, Northpoint, the company which developed Compass, they still maintain semantics, based on semantics, that they have a different notion of fairness against which their system is fair. So we want to understand what exactly they're talking about. Simply, you could write individual fairness as like a very simple hyperproperty-ish, right? So you could say individuals differing only in their protected features like age, sex, race, and so on. They must receive equivalent outcome from the system, right? Or some hyper-specification. Third example is from the legal critical systems, right? Here I would take an example which is close to me. It's filing the taxes in the US, right? It's a really complicated process. People tell me that 20 years back, you could do them manually, but it is impossible, right? How do you do manual tax filing? You get a calculator, you start thinking about, what you have done over the year. This form changes 1040 every year. There is a new clause because our socio-economic conditions, they are changing. We have cryptocurrency and whatnot, and then they are doing their best to kind of incorporate all of them in our tax system. If you have to fill it, you would realize that do you really, qualify for certain credits, and you would go and read certain form. If you do qualify, you have to write some other form, get a number from that form, and put it back in the original form. And as you could see, if you have more interesting means of, you have some gains from, let's say, cryptocurrency or stock, this would get completely impossible. And it's not surprising that now tax preparation software is like $11.2 billion industry in the US, right? On the positive side, there have been some efforts in developing free or open source options for low income individuals, right? These are simple software, and there is individuals like you and me, we have been developing this, tax preparation software. That is a nice effort. On the other hand, what happens if you're using a tax prep software that has a bug inside? Who's responsible? Is it the software developer or is it the person who's using the tax prep software? Right? In 2013, we had this ruling that says that software bugs, they are no excuse for accuracy-related penalties to individuals. Right? So if you get audited, you cannot say I was using a buggy software that was not formally verified.
You go in prison for that?
Huh?
You go in prison for that?
You might not go in prison because, but again, you might go. I mean, you may have penalties, not to pay. So, some people can go depending on what bug they were trying to explore. So that makes this tax prep software a legal system.
Question: can you pay for tax?
Yeah, they will give you $500. They will give you money back. Yeah, even if they have a bug, the best they would do is they would get the money back and then they would provide support. But if there was a bug in their system and then you get audited, it's not on them.
The money you made is payments compared to.
Yeah, I mean, it's like you pay $500, $20, and then you'll get that back. But then the trust that you had is broken forever, perhaps, right? So, why we went for this software? It's a legal critical system, as you could see, but then we don't want to kind of go with other legal critical systems because we don't want to get sued. So this is like a easy system to kind of handle for us. How do we find bugs in such systems? So my PhD student now is a faculty at UT El Paso. So he looked into this instructions and kind of read a bunch of simple properties and tried to come up with something which looks like a hyperproperty. Bunch of those really, right? So it says things like if you are a senior or you have a blind spouse, you are supposed to get certain credits, and then you could kind of come up with like more what we call it metamorphic specification or hyper specification, right? If we have an individual, if you have a person and then another person which is a counterfactual individual of you, which is exactly the same except the blindness of your spouse or the age of your spouse, then you should be paying fewer taxes if everything else remains the same. You could write this as a kind of hyper specification of some sort. And in fact, using a lot of these specifications, we kind of did some testing for open text solvers and found number of bugs. More about this later in this talk. So we have seen three different domains. We have seen privacy, we have seen fairness, we have seen law, we have seen their specification, and there is a common thread between them, and these are hyperproperties, right? These are all hyper specifications that you need to write for them. These are quite simple ones because of kind of you have seen that system that we were considering, they were more functional in nature, but you could see that if you have a legal, critical, and dynamical systems, these properties would be exactly hyper. So that is like the motivation part of my talk. There are three parts in the rest of the keynote. First, I would discuss safety and security for cyber physical systems and discuss some of the technical approaches that we could prove something about these hyperproperties. Right? Then I would touch upon fairness specifications, and we would look into, what are the opportunities for us as a community in looking into more interesting fairness properties, and perhaps give you some hint towards how to make system fair without touching the sacrosanctness of the data that you are learning from. And then we will discuss legal specification in more detail. This work is a collaboration with my colleague Majid Zamani, our PhD student Vishnu Murli, and Mahati Anand. Because of my prior work, the flavor of this work is this functional certificate-based approach. And that's a beautiful idea, right? So you could think of really in testing, you're searching for a bug in the system. In functional certificate approach, you are searching again for some parameters, but those parameters, they don't give you bug, they give you proof of the correctness. And it's like beautiful search-based approach to find proof. That's quite nice. This is a slide that I have to put. It's about cyber physical systems. Cyber physical systems, they are like nice interconnection of between discrete system, computational systems, and your physical systems. And these are connected over network, wireless or wired. And this network leaks information. Typically, we are interested in safety critical CPS, and these are already so awesome. These are large scale, interconnected, heterogeneous components inside. We have complex requirements that go beyond traditional control theory specifications like stability or safety to more interesting specifications that would require LTL and whatnot. Simple properties, as Tom would tell you, these are already undesirable in this case, right? On the positive side, in last 20 years, our communities have been working powerful deduction and abstraction-based techniques to prove properties about these systems. Then we have security critical CPS, right? Interesting part with the CPS, because we have the physical component, they expose multiple novel attack surfaces, right? You don't have to, you do have to bother about traditional side channels like time and space and electromagnetic radiation. But then you have other physical variables that might be leaking information like temperature of something or pressure or any other continuous variable that you may have in the corresponding system. So because of that, of course, this problem still is undesirable. As you could see, it's like the one is LTL, this one will be hyper LTL, and it's even more undesirable, right? On the positive side, we have rich history of security analysis in discrete event system, in software security and so on, and we could learn from that. We have concepts like entropy to kind of quantify information inside something. We have notions like opacity in the discrete event systems. We have hyperproperties thanks to you guys. Right? So let's take a quick example here. This is a simple example on, and using this example, I'll talk about the attack model. Right? So imagine a simple situation where you have an intruder, and this is like a smart city in some senses, right? You have two initial locations. One is hospital, other one is bank, and you are writing the whole, decision support systems for cars to move inside that system. Right? These are your confidential start location because you're starting from a bank, and perhaps you have money inside your vehicle. The first one is non-confidential. And in the city, there might be certain sensors, and the intruder is kind of listening to those sensors really. And I just cannot see everything, but it could see wait, yellow, wait, yellow, right, and so on. So they are seeing some sequence of observation, and you would like to make sure that they are not running anything, whether you are starting from a bank or you're starting from a hospital. Simple to our example, we have a dynamical system on the right, and then we have an arena that looks like this. We have, like, think of these are different cells really, and you have cardinal directions to move, let's say, that is your plan. So if you want to come up with your mission objective, that is maybe, let's say, you have to visit infinitely often this parking location and the key location, right? And that is your specification. No matter whether you're starting from 5 or 17, and I'm writing this start symbol to say these could be potential states. One is secret, one is not secret. Then you have your security objective, in this case capacity, and you could read what exactly is going on. This is like one of the common ones. For every trace, there is another trace, such that both of them are initial. One start with the secret, other start with the non-secret, but they must have the same observation. Right? Here is one plan that you could come up with. Right, the first one from the state 5, you could go chick, and then go keep on moving between P and Q forever. Starting from 17, you can go to the Q, and then go between P and Q forever. And using that, you satisfy your mission objective, of course. Right? But then you can also see that security objective is not satisfied. Here, your adversary is seeing, intruder is saying, well, white, green, white, green, white, green, white, green, white. Here you would see white, green, white, green, white, green, white. And something is being inside. Right? That you know there's different signature. On the other hand, you could find the following schedule from 17, which would be white, green, white, green, white, green, white, and that would match exactly the other one. So for this particular system, it's possible to satisfy both your mission objective, your security objective. Right? We are interested in, of course, you would be interested in synthesis of this kind, but here I'll talk about verification. Here is a problem. We are given a discrete time dynamical system. We are given a hyper specification, and that is kind of quite neat about hyper LTL. Right? It allows you to kind of stay both together. You have your LTL specification, you have your security specification. You can put it together and write this hyper LTL product. Right? So we would like to make sure that system does satisfy my specification. Right? It's already undecidable, as we have talked about. Interestingly enough, this work by Pavel Cherny, Rachel Balur, and Steve says it shows that classical abstraction for cyber-physical systems, they don't preserve OS. Right? My colleague Majid Zamani and collaborators, they have been looking into opacity preserving abstractions. So you have a cyber-physical system, you would abstract that into a finite state system in such a way that you would preserve some of the opacity properties, and then you would use finite state hyper-LTL model checkers and so on to do properties that you could kind of transfer back. I would not go into that. Here is a kind of a link that is a beautiful set of work. One of the problems with those work is that we have the state space explosion, right? Problem. So unlike that work, I would more talk about today deductive verification, which is like find a search for a certificate, and that is a proof that system is correct. Right? We call this deductive verification of functional certificate-based approach. Here is a recent paper coming, appearing in TAC soon, but we have an archive for that. So let's take I'm not sure how many of us have seen some of the work on valid certificates, quick and good. So what I will do is like give a quick tutorial on how to use valid certificate to prove property about the system. These are not hyper properties first, and then we will extend them. Right? We have 3 interesting ideas. The first one is variant certificates. If you have seen state invariants or inductive invariants for your states, you could think of variant certificates that generalize that in some way. They're functional analog of those inductive state invariants. Then we have Lyapunov certificates. These are like a functional analog for ranking functions. And more recently, we have been looking into notion of closure certificates. These are inductive transition invariants. Right? I'll talk about that more. But let's first look into what is the definition of my system. And everything is visual, really, right? Nothing. technical. We are given a system which we call a discrete time dynamical system. So control the discrete time, but then the environment is continuous. So we have a discrete time but continuous space system. Right? You have your set of states, you have your set of initial states x0, and then we have transition function which takes a state and then tells me what is my next state. Right? Doing so, I will start from initial state and form these traces of the system. And then in the safety specification, you may want to make sure that all of the traces that start from initial state, they don't touch your unsafe set of states. Valid certificates, if you can find one, allows you to do exactly that, right? How do we verify safety using valid certificates? Quickly, what are these valid certificates? We know what is our inductive state invariant. We would define like so. Valid certificates, they are functional analog of that. So if you find a function such that the zero level sets, they are exactly your inductive state invariants. More about that with the picture, right? So you are given your system, right? If you can find a function B, which is from the state space of your system to reals, that has the following property. So think of this really. I'm showing you the label sets of my barrier certificates. Maybe here for all of the top layer, it's your barrier is positive, and as you go down and down in this lake, barrier value keeps going more and more negative, right? If your initial states are such that your barrier is already negative, and with every transition, your barrier decreases, then starting from negative, you could never go to positive. If you know that your unsafe states, they happen to be in a region with a positive barrier, then you have shown that your system is safe, right? So you are looking for a function from state space to reals that has these three properties. B is non-positive in the initial states, B is positive in the unsafe states, and B decreases with every transition. There are different versions of those things, which I'm not going to, but at a high level, you get the idea really that what we are trying to capture. And you could already see from this definition that by existence of barrier certificate characterizes safety. Question.
You assume the notion here that when you're getting closer to the unsafe set, that the score will be monotonically increasing as well, or?
So, I mean, in this particular case, we don't need to do any discrete time. We're looking for discrete time. There is continuous time and a log of that where you have to say something about the boundary of your unsafe set and so on. Right now, I'm kind of taking this simpler. It's not all that their certificates include, but this is a good definition for a discrete time continuous space system.
You're either in or outside.
So here is like kind of really straightforward. This is positive, this is negative, and with every step, except for the unsafe states, everywhere else, you take a transition, you get a decrease. You could come up with more interesting notions like K barrier certificates, and it's a lot of interesting opportunities in this. Okay, how do we find these barrier certificates? Now, what we have seen, if you can find a barrier certificate, we have shown system to be safe. It's like exactly like testing. If you can find a bug, your system is unsafe. If you can find a barrier certificate, your system is safe. How do you find it? There are powerful approaches. First one is by Prashna and Jarababe. Right? It's based on sum of square programming. So it makes some assumption about the system. If you have polynomial dynamics, if you have initial and unsafe states could be written as polynomial semi-algebraic sets, right? And you are looking for barrier certificate of some polynomial template, right? Then at these constraints on barrier certificates, so you could kind of fix some template and say I'm searching for a barrier certificate of this shape really. These constraints could be imported into having these polynomials as positive. Or you could use sum of square programming to say, well, these polynomials, I will not know if they're positive or not, but I could show there are sum of squares, then I'm good as well. And these are quite performant approaches. So that's a very interesting approach of sum of square programming to search for a barrier certificate. Other approaches would be based on optimal control theory. You would come up with some optimization objective, and minimizing or maximizing that objective would give you optimal barrier certificate. My colleague Sriram and his group has been working on this counter-example guided inductive synthesis for search of barrier certificate, the outcome of certificates, and so on. And finally, Tom and his group has been working on also neural network-based verification of barrier certificates. Right, so there are a lot of interesting approaches, especially with the neural network. I think we have a potential to really technically scale the search of neural network of the barrier certificate discovery. So that was quick tutorial on barrier certificates. Now, how do we verify opacity using barrier certificates? Right? It's like a simpler version of your hyperproperty. So I'm interested only in this property, which is an opacity hyperproperty. Right? You have only one quantifier ordination. We would try to generalize that later. Okay, so again, with the picture, we have our system. We have initial states. We have two kind of initial states, not only two, but two kind really. So I would break this at maybe top one would be green, bottom one would be red. These are your non-secret starting states. These are your secret starting states. You want to show that for every choice that for every choice of trace from the initial non-secret state, the sequence of observation that you would get is possible to mimic them from the non-secret starting states. Right? And that's what we would like to get a proof for. We would like to get a kind of local proof for that fact. Here are the classic hyper-LTL semantics. You have like two versions of the system you make, right? One of them starts with secret initial states, other one non-secret initial states. And you could think of it's like a game going on between universal and instantial player. Universal player goes on and chooses an omega run with some observation. Looking at that omega run, exist player chooses another omega run that matches the observation. If you can do that for every omega run starting from in the left side, and you could match that on the right side, you are winning as an exist player. Otherwise, you lose. To capture the verification condition with the barrier certificate, we look into slightly more restricted semantics, what we call turn-based semantics of this thing, right? Instead of saying for every omega trace, there exists another trace, right? To say, for every, we look into turn-based setting, right? Starting from initial states, for every choice that universal player can make, without letting go of what they're going to do in the future. I don't want to do that as a legacy player. Right? Just choose. If not even seeing what they would do in the future, I could choose an action, right, to match that observation. Then for every choice from there, I can match an observation. From there, every choice, I can match an observation and so on, right? So you could see that if exist player has a winning strategy, letting go of seeing the future already to win, they would win with the classic hyper-LTL semantics. But good thing with this kind of notion is that it allows us to kind of have a local certificate on it, right? How do we do that? So again, here, winning strategy for exist player under turn-based semantics imply the one under standard semantics as well. We would capture this willingness of the exist player with barrier certificates that we call augmented barrier certificates, right? So a certificate for turn-based winning of exist player, right? So what we would do is that on the self-composition of the system with each other, right? You could think of what are the safe states. Safe states are those in which two copies they match the observation. Initial states are those in which they match the observation, one is secret, other is not secret. Bad set of states are those in which they do not match the observation. Now you could think of for the pair, you could write a barrier certificate, right? Negative in the initial states, positive in bad set of states, not matching observation. And if you can find, yourself decreasing at every step, you could show that you're satisfying hyperproperties.
So what you're saying is that for every move of the for all player, you get kind of barrier certificate for the existential.
Yes, so here is exactly that. Right. So here is like a slide animation for that. We have a self-composition of the system. Now X process, X field, right? With the initial states where the first one is X0 intersection safe states, the other one is X0 minus safe states. So we call that X as X not X, right? And then you have this kind of a set of states which are matching the observations in both of them. You have initial states, you want to make sure the first condition, right? That barrier is non-positive in those set of states. right? With the matching, of course, the initial states would be with the matching labels here. And then you would say that these are your unsafe states really, right? And in the unsafe state, your barrier is positive. And then you would show that this is the interesting part. For every pair of states X and Y, for every choice of in the first copy of the system, there is a choice in the next copy of the system. So that if my barrier is negative, I would keep it negative, right? Or in other way, if my barrier, I would decrease the value of the barrier certificate in the next, right? And if you could do that, you have to make sure that you are writing the conditions properly. But once you do that, and you can find a barrier certificate, here is a proof that system is opaque.
Just to understand better, when you turn it into a true-based game, you bring no prophecies before. You force no prophecy disclosure.
So it's like knowing how to picture.
Yes. I'll come to that point. So I'm letting it go, but we want to generalize that too. But for now, we have something, right? In the next step, I will show you how do you kind of handle some of the prophetic situations as well, right? After this slide, so I will get back to you. How do we discover augmented barrier certificates? Is the same approach to right? So existence of an augmented barrier certificate implies opacity. We could use sum of square programming. We could use neural networks, really, right? So I think in some of these works, really, we are using neural network. In one of them, we are using sum of square programming, right? And you could use also counter-example guided inductive synthesis. There are not many papers in this domain, so we have some very simple examples, really, 2 or 3 very variable ones. But I'm hoping that with the neural networks and interest from the community, we could scale that like we scale safety. We'll see. You never know. We don't have to tell that. Okay, how do we generalize that to hyperreality? And there is a nice paper by Ofuk and his group, right? Automata theory meets barrier certificates, and it's quite neat idea, really, right? So if we have like instead of barrier certificates for safety, if you want to extend that of omega regular property, you could come up with your Wiki automaton, and that you would have multiple lassos in the Wiki automaton, right? So think of like every sequence of transition in a lasso. If you can think of this transition, the arrow is wrong here, it should be that side, right? So let's say I can go from this state to that state, from there to there. The first transition is based on some atomic proposition, second one on some other atomic proposition, right? If you could show that if you are in this atomic proposition ever, then you would never be able to see those atomic proposition. You have essentially used the scissor and cut that transition. So if you can cut all of the transitions of for every lasso, if you can cut, that somewhere in between, you have a proof that it's not, that you have a proof against that omega regular specification. So it's an interesting idea. Again, I could say not very elegant way to capture that, but if you can find a better certificate in this way, you could show the safety. We have used the same idea to kind of break that with the augmented barrier certificate. And I take my word for that. We have seen only 2 quantifier alternations so far. But if you have multiple alternation, the whole idea behind exists layer, not seeing the future, and universal layer anyways using all the options over there, right? If you have a winning strategy, you continue to have winning strategy there. Details are in this paper.
But the number of APCs that we need to find is exponential in the size of the phone, right?
No, not published. No, but this is a big expensive problem. Yeah, you're right. Okay, as you mentioned before, right? Augmented barrier certificate approach is not complete. Here is a very simple example. What does it mean? We have 2 initial states. This is secret state and this is non-secret state with a single observation. Now you could see that for every choice of your universal player, either you could go on the top, which is like sequence of O's, the bottom one, eventually not O's, and so on. For every trace, you can find a trace over there. On the other hand, you cannot find them just by looking locally. Right? You need this omega regular locator or some locator of some form to be able to win that. So is it possible to kind of capture the notion of, what all states we could reach in the future using some kind of a function certificate. That would be quite interesting if we can do that. And our idea is that of closure certificates to capture that. What are closure certificates, right? Closure certificate is something that we have recently introduced, and it's a play on, how you have barrier certificates and a closure certificates. Closure certificates, they capture your transitive closure, right? So you can think of your inductive transition invariants, right? So if you have like all of the ledger transitions, they are in the inductive transition invariant, and then you have like some pair of the states they are in the inductive transition invariant, and then you could make a concrete transition that would be the inductive transition invariant, right? Closure certificates, they capture that using a function. So if for two states X and Y, if my closure certificate is positive, and I'm saying that if it is positive, you could reach from X to Y. If it is not positive, you're definitely not reaching it. Right? So it's like one-sided, the over approximation of your transitive closure. Using closure certificates, you could prove things like finite visit. Slightly, I would say, more elegant way to capture what we've seen before of cutting the transitions in your Buffy, right? Let's say you are given initial states, you have four Buffy condition states in this set you want to visit finitely often. How do we do that? We would write a closure certificate over for every pair of state. I want to show that if there's a transition from X to Y, which is X of X, that should be positive. In one step, I could reach already, right? And then I would say, well, if something is positive, if from the state Fx I could reach Y, and from X I could go Fx, of course, then Xy should be positive as well. And that kind of captures your inductive transition invariant. Second part is like a ranking function like condition. For every initial state, for every visited finitely states Y and Y prime, if I could show that, if Tx0y is positive from initial state, I could reach some state Y, and then from the state Y, I could reach some state Y prime. Then, so again, initial state, I could reach two states maybe in the visited finitely part. Something should give, right? So it's like something should decrease at every step. If I would go from here and then I reach again, my transitive closure, the value of that decreases by some amount. It means I cannot forever keep on decreasing, right? So it's like ranking function kind of conditions. The first one, transition variant, the second one, ranking condition, together they would give like point visitation. Okay, so here is the idea. For opacity, what we could do is closure certificates, they can capture your arbitrary finite look ahead, as you were mentioning again before, right? Before I was saying, don't even, Explainer is not even looking into the future. We could slightly extend that to say, well, I would buffer the states, maybe 2 look ahead, 3 look ahead, 4 look ahead. With the closure certificates, you could see what Explainer is doing some kind of over approximation of what states will be reached. And if looking at that, I could choose my local actions and I win, right? So it's like some kind of a over approximation, but we still do not know. So it's like a very early work really, that if it is complete, if you need omega error look ahead in this case, really, right? I mean, with the transition variant, you would check every finite connectedness, so to say. So would be interesting to extend this idea. We have no idea right now. And that was only for opacity. We do not have any notion of under approximation of transitive flow, inductive transition variance. And we would need that if you want to handle arbitrary hyper-LPs. For universal layer, we want to over approximate it. For illustration layer, we want to under approximate it, over approximate, under approximate, right? So that's an open problem. What is the notion of under approximation? Can be combined under and over approximation for hyperproperty, for closure certificates to come up with a complete way to capture hyperproperties. And then, of course, how do we handle asynchronous hyperproperties in this case? So that finishes the first part of my talk. That was the technical one. These two are slightly non-technical, but I would hopefully motivate that there are more exciting things in these two directions, right? So the first one is, any questions about the first part? Quickly, I can take. Yeah.
You can go out to the omega value.
This one?
The feature was the last thing. You were not, you weren't sure about the
Like what?
omega.
I have a,
I think the last slide.
okay. Sorry for that.
Yeah. Yes, so what I suggest to do first is to take the only theory of Raphanian traces and try to see whether what you have already is complete for that.
Mhm.
Because I'm not sure about the omega loop effect.
I don't have a proof.
You
So
are
say
sure.
I agree, but I don't have a proof for that, right? So, maybe you need only,
What I'm suggesting, before you go into omega for omega traces,
Yeah.
you take the low chain confinement traces and try to see complete. Are you ready?
that does make sense.
Because
You are right, yeah.
Your side physical
Yes.
system is not supposed to be one.
Yes, that makes sense. That makes sense. Right, so what you're saying is like, if I could take like a LPLF kind of variant for that, that's-
Then you try to see whether what you have is.
yes, that does make sense a lot, yeah. Thanks. Okay. Other, feedback, tips? Questions?
I mean, on asynchronous hyperproperties, in my opinion, like the idea would be to, you know, look at this dynamic warping stuff. Because like there is a lot of literature in the past about, you know, how to align sequences of signals, right? And I mean, for free somehow.
Yes,
It's
yeah.
already there. And all these metrics, how to take one signal and the other and try to match one on the other, and I think it's like the thing that one needs to look there.
Yeah.
I'm not sure whether that is possible to do anything.
Yeah, I
In
think
terms of like, I think it's more like the direction would be more monitoring than doing any model
yeah.
analysis, because I think it's not possible to do it.
Okay,
That's my.
Yeah, we will discuss
feeling.
more, right? Okay, so the second part is about fairness specification. It's more like what I have noticed from my work in software engineering, some of the opportunities that we have for our community on hyperproperties here. This is the work with joint PhD. Said Ispas-Nihari, who did a PhD with power churning, and me. His PhD student, Beria Manjasi and Genkan from Penn State. So this is some of our work in HC on looking into this fairness specification and finding bugs for this. Right? Coming back to the example that we have seen earlier, and as I mentioned there, that kind of the company that developed that complex software still maintains the fairness. If this software is still being used because they have different semantics of fairness, right? So there is a debate over what should be fairness semantic. Northpoint does not agree the result with that analysis. So let's understand how to define fairness. I'm using Compass as an example here. We have a neural network that has certain inputs. These inputs could be partitioned into two parts with protected or sensitive attributes like race, age, and sex, non-protected attributes like age when you did the first prime, violent history, and so on. And based on that, you are going to get some score of your recidivism, like how likely you are going to reoffend. The first notion that a lot of US government organizations they take is that first one, which is fairness through unawareness. What does that mean? If you're training a data on input and output, and you say, I'm not even looking at the race, I'm not looking at the race, age, and sex, and then I'm doing the training. And that looks like a good enough way to ensure fairness. But you could kind of agree with me that there is like a high correlation of other features from age or from sex and race and other things. In this case, in the US, your zip code can tell a lot about your race. Then there is other notion is known as fairness through awareness, right? Two individuals with similar qualification should receive similar outcomes. It's a very popular type of property over there. If their qualifications are similar, their prediction should be similar, right? Of course, measuring qualification is really hard. How do I find one candidate more interesting than the other candidate? Right? We don't even know sometimes. Anyway, it's a difficult problem. You can take two different people and can never compare them. So for that reason, people propose this notion of causal fairness. What does that say? Assuming everything else stays the same, changing a protected attribute should not change the outcome. That makes sense. For example, for all the persons X and Y, if X and Y, they are similar in everything except sex and race, prediction of X should be same as prediction of Y, for instance, right? These counterfactuals, you can find bugs in the system of this form, but these counterfactuals, they may be unrealistic and conservative. For example, you would say, well, I have one individual who's 40 years old with 2 children. I would look into the counterfactual, which is 5 years old with 2 children. That doesn't happen. So you can find a lot of bugs that might not be, relevant. Interestingly enough, we looked into the work by Boris and David Bassin, where they have quantified information leak using entropy, and we were like quite inspired by their work. So what we did is we introduced the notion of that kind of information theoretic fairness. So you could see like how fairness and secret, they are very similar. So here we are using like an entropy-based measure to kind of quantify how much unfairness is in the system. And we think that having that, quantitative notion allows us to search better, allows us to present the bugs in more interesting way. If we have like 1,000 bugs, it does make sense to show which bugs are kind of shown before to the developer than which other bugs. So think of an individual for which the system is highly unfair. They have multiple features, and you change any of those, the decision changes by a lot. You may want to see that could be a bug in the system, right?
Sorry. So these facts, what do they include? Do they include household fairness?
Positive fairness.
Even this impossible calculus.
Yes. There are ways to get rid of impossible things. You could take some kind of, like the notion from causality to say, well, age more than something causes children to be had, right? Those kind of things. So there are ways to kind of fix that problem. Other notion of fairness, which is again a good opportunity for us, is group fairness. Instead of saying an individual is being treated unfair, you could look at the whole statistics of groups, to compare them. For example, you have I would just skip those things. You have equal opportunity difference. You want to say the difference between true positive rates of different groups should not be 5. And we have this average odd difference. The average of differences between false positive, true positive between two groups should not be 5. I have the feeling that group fairness notion, which has not been studied with hyperproperty lens, but there are a lot to kind of say in those situations. Right? Here we would like to think of like 2 different inputs, and maybe you could quantify with some cost as the system goes through that, and you want to say average between these 2 situations would not be far enough. So I have not seen any of this kind of notion being defined for a dynamical system and connecting that with the group fairness. So that's an interesting opportunity, I think. Fairness testing, software engineering community has done a lot of interesting work. I think started from 2017 by this tool called Themis, and that is looking for this bugs for your hyperproperties of fairness kind in your software system. These tools, they're using fuzzing to really scale to awesome large systems. I just kind of put all of those references together in case you want to look at those works. Once you find a bug in the system, the second aspect is how do we mitigate that bug. There are 3 different ways to mitigate those bugs. The first one is in the pre-processing. What does that mean? So you have a system, you find a bug, and it's that is unfair. Let me fix something. And that could be a very dangerous situation. What do you want to fix? Do you want to fix the input data, but the data is sacrosanct in machine learning? Do you want to do post-processing, that you get the model and slightly modify that model? But that looks like something wrong. Final thing is in processing, maybe you want to change an algorithm slightly, but that would require non-trivial expertise from user to understand how to change different machine learning algorithms to take different kind of specification into account. Right. So there are these three works which I hope they come from these three different ways to handle it.
Sorry, one piece.
Yeah.
Like, there is also another way. It's not, you don't change the data, but if you have a bias in the data, you try to sample the data in different ways.
No,
Because
but that's structuring the data, right? So
I
there are
mean,
all
if you are sampling all in the same zip code, I mean, all the people
Yeah,
in the
I
same
mean-
zip code, then it's almost bias. So
Agree.
it's like,
yeah, yeah.
so you need to,
data
you
sampling
need to
is
know, like, how
I
to
see.
sample the data. I mean.
true, yeah. But that is like a very challenging problem for us computer scientists. So I have a suggestion here. Can we improve fairness without compromising on accuracy? Right? And we have some levers there in machine learning algorithms that you call hyperparameters. Wouldn't it be nice that if you are trying to train a system, just by changing the hyperparameters, you get the same accuracy and you get better fairness? Why don't you do that? Is it possible? Right? You see what I mean, right? You have immense freedom. If you are training a decision tree, how deep the decision tree should be. If you are training, some clustering algorithm, how many clusters? What kind of loss functions you would like to use? What should be the number of layers in your neural network and so on, right? There are some parameters that consistently are unfair for some reason, because you could see that already, right? If you are trying to learn a decision tree, which is quite shallow, that would find the most discriminating features. In this work, we have indeed this work, we have taken a bunch of neural networks. Yeah.
Without compromising on accuracy, that sounds strange to me, because
Yeah.
lots of biases are in the training data. And then if you evaluate the accuracy of the model, you would evaluate the performance on some test set that may contain the biases. So if you really want to get rid of bias, maybe you need to sacrifice it.
Yeah, but that decisions we cannot take as engineers.
No.
Right, but here we do that. I mean, it's like your choice really. Some random software engineer sitting somewhere, they say, okay, I use 5 and 7 right now because that's in the manual. Right? They can change it. If they know already that I don't want to get sued, for example, of showing the system to be unfair. On the other hand, I don't want to change the data set or the way that we are, So just mentioning that as an engineer, we have some levers already. We can play with them and do our job to make sure that systems are always fair. But you are right. I mean, these are more systemic problems that the problem is typically somewhere else.
So I was actually thinking exactly the same, right? So the data, as you say, is just reporting what is already there in lights, right? So maybe a different approach is that why don't we accept there is this bias, right? There is this problem in society, let's call it this.
Yes.
And what we do is that we query the machine learning differently, right? So instead of querying, with the user, if I say it's like individual, I know there is this bias.
Yeah.
So why don't I do multiple queries to the machine learning and do like somehow composition of all,
Yes,
separate.
that does make
So
sense.
that's a different approach, because I think even with adding layers,
Yeah.
again, these biases are there, so it's like.
No, that
it
does
just
make
has to be
sense.
separate.
So you may want to say that maybe I have like some kind of Pareto curve for my fairness and accuracy, and then I want to kind of allow people to choose a point over that. And that does make sense as well.
Or just have multiple samples, so with the same individual, we do maybe 5 queries with where you hide some of the features and then
Yeah.
do a compose, compose this according to some fairness, for
Yes,
example.
yes.
Or the other things that I just came up is the fact that, you just say, look, this, you do the prediction, and then you say, look, you verify that this prediction is unfair.
Yes.
And then like it's up to the person to
It's
say,
kind of a very
look,
politically charged question. You will say, I have the data, I found it to be like this, and then I want to change it because according to my definition, it is not fair.
Yeah, because the data.
And then it's like all of those situations like, diversity, equity, inclusion, issues that they're going on, that you are unfairly trying to modify the data because that you want to do something, right? Those could be, they are serious, important questions, but if they are beyond my pay grade, I could at least change the hyperparameters and do my job really, right? And what we have shown here is that, in a lot of situations, this is all you need maybe, right? So if you have, like, just not blindness cause unfairness in the society. So if you can, choose the parameters carefully, you could remove some of these problems, but of course, this is not the kind of all solution for that problem, which is difficult in that, as you notice already. You can go to this website and you can find some of the benchmarks that we have used. This kind of paper uses all of the, I think it's the, bunch of neural networks that we mentioned, like compass and so on.
It's more of a social science question of,
Right.
okay, you have your data.
Yeah.
It functionally determines that.
Yeah.
And then you don't want it to functionally determine what it does.
Right.
And then you have to choose which of the things you don't want to functionally determine something. But it could be that, for example, if one would become a basketball, then in principle, if you are tall, then you are probably being selected more likely. And then probably if you have different genetics, then it determines the height.
Yeah.
So in
the
principle,
question is.
how can we
Which parameters you keep?
yeah, which you keep, which you didn't already.
But the interesting thing is that with the formal specification, they can formal specify these and then maybe two, let's say, right?
Right.
According to your definition of what's fair.
No, at least, I mean, what I'm saying is that we have to think about those questions, especially as a hyperproperty community, what specification they look at price fairness, right? Which is like every party, concerned party is buying into that. I thought people might ask the question that, oh, well, these are neural networks, really. I'm developing cyber physical systems, software systems. These are more dynamical systems. Why do I have to bother about those things? On the other hand, with the neural networks in our dynamical systems, this is our problem, right? Here is like some nice, interesting situation that you could see. Is the historical fact that in the US, it's more dangerous for Black individuals to cross the road than otherwise. 3 to 5 more likely to die, and that happens. Why that happens? You could say, well, it's a social problem. People, Black, white, alike, they are less likely to yield for Black pedestrians than otherwise. Right? And it's not just they don't yield, and they have kind of did very quantitative study, like how far, if a white person is crossing the road versus Black person is crossing the road, how far cars they stop, and that was more indicative whether they crossed or not. And this experiment was from I think University of I would say Oregon.
And then done the study on both cases, like Black against white and white against.
No, so they did not control individuals who were
Yes, it
driving.
would be nice to see also the Black.
That could be, but it just saying for the population in that particular district where the data was collected, right? But yeah, that makes sense, of course. So you might say that I'm learning from the way human behave, really, right? And you might be collecting data as an Uber or something, right? And you say, oh, when people drive like this, the machine will drive like this, I'm mimicking the humans, right? So those again then will feed into our autonomous driving systems as well, these biases. I read this paper more carefully. I want to use this paper as an example. That, oh, well, this is my story. Paper says something really positive. Right, so they found a lot of autonomous driving systems, and they found no proof of discrimination with the race. They found that age-based discrimination is there, which is like doesn't make sense because children, they're crossing the road, you cannot see them, and that is their female discrimination. They found out also, like if a person is crossing the road, or a man is crossing the road, there is a different timing. But that is also very different globally. If you go to, let's say, Australia or New Zealand, you would find that women, they cross the road and people stop, and when they're crossing the road, they don't stop. So it's very social phenomenon that they find. Here is a nice paper, really. They did fairness analysis of autonomous driving system. all I want to say is that we have facts, we have social behavior that gets codified in our autonomous systems, and we have to be there. Finally, I'll take 5 minutes, maybe already over, to talk about, or 2 minutes, maybe talk about legal specifications here. Work with Said discussed the area, and then we have legal experts and psychologists experts over there, and we have experts in designing human systems. So let's go back to the previous case. Right? How do we detect legal critical bugs in legal critical systems? What are the challenges? The first one is this absence of oracle. What does that mean? Oracle is like if you have an input, you want to have an ideal output for that. I'm looking for, let's say, what is square of x? I will give 2, I want to get 4. Right? I have an oracle. But for legal systems, to get an oracle, if you think of tax prep software, you need to have like a tax expert telling you this particular person should be paying this much taxes, or we need legal or other things. We don't have data sets. We have, even if you can get data set of some form with the permission, that would be computationally feasible. How do we handle these systems? Because it's a legal critical system, it's based on which I learned common law, like all of the legal systems, or most of them around the world. Right? And there is a central doctrine of your common law system, and that is legal. It's a doctrine based on legal precedents. If there is a precedent, you could refer to that. Right? So this is known as in Latin stare decisis, or let the decision stand. So courts and judge, they must honor the precedents or the decision rulings and opinions from prior cases. If something has been done, typically lawyers do make the case that, oh, well, this is similar to Smith and others from 80s and so on, and hence I should get a similar proceeding. But for us, it's an interesting corollary that you would, I hope you can see that from there, is the correctness properties for legal system can also be defined in terms of relating similar cases. You may not have ruling on the other case, but you know that if 2 cases are very similar, you know the output should be similar. And that's a hyperproperty. Right? And that allows us to have a large class of hyperproperties that we could pose about legal critical systems. That's what we did. We took in the whole tax prep software. We studied different conditions when you get credits. And for each of the credit conditions, we came up with this hyperproperty. A senior over this age must receive similar benefits as a person without seniority, right? And you could write this specification, which is for every individual X and Y, they have the same age, or they are same except the age. One is senior, other is not senior, and it is the output I should see. Said and his students, they went meticulously trying to get the requirements in various domains like disability, PITC, and so on. More recently, we are also looking into using large language models to kind of read that text description and try to get this metamorphic or hyperproperties out, and then manually validate them. Of course, we see if we are getting it right. We did these specifications. We use text prep software, and then we use like a search base or fuzzing in some sense for those metamorphic specifications to try to find the bugs. Once we find the bug, we use simple machine learning to explain what is causing that bug. And here are some of the bugs that we found in the text prep system. It had the open text solver had multiple missing eligibility conditions. It had unexpected outcomes when your tax return, they were getting close to 0 for some reason, right? They were applying itemized deduction when expenses they were less than that, and supposed to not apply that, right? Itemized deduction exceed a standard deduction, but resulted. So this is like a very technical incorrectness in the system. So we found these 4 bugs purely from hyperproperties, purely from buzzing the system and trying to see if it is doing correct. And the person who developed the open text solver, they took our bugs and they really fix those things. So yeah,
question, small question. Can you go to the what the I really formula?
Yeah, it is.
No, the next one, where the teaching.
Okay, sorry.
like say this, for example, I think you're supposed to say, like set the target, everything else remains the same.
Yes, that's the semantic of this thing.
Oh, that means everything else.
X is same as Y except for the X.
Except, okay.
So that's, I mean, it's like a cute way to show, but yeah, there is a different meaning on that. It's like maybe slightly less intuitive.
No, fine.
Yeah,
I mean, all your properties are for all, I mean, or you are also for.
that is another interesting thing, right? So we were,
Because otherwise, like, you don't really need that properties, right? It makes some sense.
I'm sure we can find more interesting properties which would require quantifier relation. It's just, we were only concerned with this, text type software in this one, and they were quite similar, yeah.
So, I mean, these hyper properties that you're giving there, these are sort of necessary conditions
Yes.
for correctness. Is
Yeah.
there, but I mean, eventually you would want that software to be correct, so you
Yes.
could even strive for functional correctness.
Yes, that does make sense, but we don't have, we do not know if that is hyper property, right? You could pose one, so once you have a legal critical system, we have shown that to be correct with respect to this very basic specification. Hopefully you could take that as a, legal code itself, and then try to query that for high level properties like fairness. You may want to talk about group fairness. Say every person from, this income group and that income group, how much taxes they're paying if there is a parity between those individuals, if there's a parity across different income groups and so on. So those specifications could also be hyper. Or in general, I'm not making the claim that everything is hyper, so of course you would need, you want to prove other properties.
I think that we work on formalizing the French text code.
Yes, I noticed that, yeah, we met with those people as well. That makes sense, they have like nice TL-based approach to do some interesting properties there.
One more question.
Question, sorry, go ahead.
As you were using these hyperproperties, wouldn't you expect that at some point you get unfeasibility? Meaning that there is so much precedence that this equality, they get actually different outcomes. Say, well, there is a case that is similar to this. but
Yes,
there is another
yes,
case.
that is possible. So again, we were doing only the testing. Let's say you are develop a verification approach, and all of this data is already on your website. If you want to kind of try that out and take a property and prove the system to be correct, and then you realize that this property holds or its complement holds on the system. Why that is the case? That would be a good feedback to policy makers. If you find something to be incorrect, or the law says that should be correct one, that's a good feedback to IRS in this case. But at least it allows us to, use our tools to say something. It's like software is like it's an artifact about the law that we can touch as computer scientists, right? And not like, well, you have a degree in law, right? And these properties, they do make sense, but I'm not saying if a system can find a bug of this form that is incorrect. It's just like we are showing the bug to the designer.
Yeah, and one thing is that if you want this kind of similarity to imply similarity, then everything must be continuous.
Yeah.
If these great things there, then. Right.
So finally, is like a last slide over here. I want to end with that. And this is like a transition from legal critical to social critical system, again with the lens of hyperproperties. Right? What does that mean? This example is really close to my heart. So here is the benefit software for Compass in the state of Philadelphia, Pennsylvania. And what they could do is a lot of people, they kind of eligible for benefits. You could go there. It's a whole process to talk about your condition and give a lot of confidential data to them. To help you simply to decide whether you are eligible for benefits or not, they have simple tasks for you. So you could go to this website, give very little things from non-confidential things, and they could tell you you are passing or not. And now you could see the situation that if someone indeed needs those benefits, right, and you go and fill this form, and then there is a bug in the system, right, that could be really rushing to you. And it's our responsibility as a verification experts to look into these systems, which you may have a black box really going on over there, right? But then you still want to prove properties. we are not bothered about black box. We use neural networks for verification these days, right? And these systems, they are looking for hyperproperty based verification of a black box system. So in particular, our colleagues from, I think it was Michigan, Nell and Nicola, they looked into this particular system and they found out bunch of errors in this, benefit steering tool. Right, so they did comparative implementation. So they looked into benefit eligibility handbook and they made their own software. And they would kind of look at their own software, search for interesting extreme cases, they try it out on the government system, and then see they verified that they were indeed giving the wrong decisions. There were two key kind of wrong decisions. Households with exceedingly limited financial means, they were given wrong decisions and they don't qualify for. On the other hand, we have like a false positive. Many wealthy and clearly ineligible households, they were given cash assistance and SNAP from the fake data that these guys have constructed, which you could look at the data in this paper of theirs and find out that indeed there's something wrong. And they did not follow the methodology of hyperproperty specification, but then you could, we are talking to them and it looks like a lot of their specification, they are very hyper in some sense. Every person who's of this form and only, so it's like, you are, you are a single mother versus you are married. In one case, you would be eligible for benefits, other is not. So we could write those kind of hyper specification and look at this kind of, software and try to put properties. So in summary, we talked about hyperproperties where we can find them in safe and secure systems with fairness in legal specifications, and they are not really, right? And then here I want to say that your research in asynchronous hyperproperties has indeed great potential to positively impact most vulnerable members of our society, right? So we are in this very crucial situation with the neural network being present everywhere, and we should take up this challenge. Okay? With that, I will complete the start.
So I think I will keep the